Now in this series again we discuss about the what is this quantum algorithm based upon the quantum walks. There are the various features which keep in mind whenever we use a quantum algorithm, in which one feature is a quantum walk. So we choose or we just suggest the algorithm which is based on the quantum walk. So a quantum walk is the quantum analog of the classical random walk, in which a classical random walk can be described by a probability distribution over the some states, while a quantum walk can be described by a quantum superposition over the states. So, quantum walk means quantum superposition over the states, where we define the distribution over the probability distribution over some state. That is the quantum walk. So, quantum walk are known to give the exponential speed ups for some black box problems. So, they also provide the polynomial speed up for the many problems. So, a framework for the creation of the quantum walk algorithm exists, and it is a versatile tool. So, first is the boson sampling problem. What is this boson sampling problem? Where an exponential configuration assumes an input of the boson or that is the photons of moderate number that are randomly scattered into a large number of output modes. So, constrained by a defined unitarity. Now, when individual photons are used, the problem is isomorphic to a multiple photon quantum walk. So, the problem is then to produce a fair sample of probabilistic distribution of the output that depends on the input arrangement of boson and R that and it is the unitarity. So solving this problem with a classical computer algorithm requires the computing with the that is the permanent of the unitary transform matrix. We do in the quantum physics, that is the unitary transform matrix whenever we solve the whenever we solve the problem which is just requires the boson sampling or the distribution of the photon values. So, which may take a probability long time or be outright impossible. So, whenever we just find out the probabilistic distribution, so we can use the various other algorithm. So, if it is proposed the existing technology, that is a quantum standard probabilistic methods of generating the single photon state could be used as an input into a suitable quantum computable linear optical network, and that sampling of the output probability distribution would be demonstratively superior using that of the quantum algorithm. But further this problem further it is investigation has been done in 1925 predicting the sampling problem that had a similar complexity for the input and other than of the Fock state photon, and identified a transition in the computational complexity from classical simulable to just and hard as a boson sampling problem, which depending on the size of coherent amplitude input. So, elements. So, here we are having the element distinctness problem, where we are having a n queries are required for a list of size n. However, it can be solved by the theta n 2 by 3 queries on the quantum computer. So, this problem determining whether all the elements of the list are distinct. This is the distinctness problem in the element distinctness problem, how we can distinct the all the element in the database. So, by solving a query, it will use the theta n2 by 3 queries on a quantum computer. So, optimal algorithm was put forth by the Addis ambience, and here we are having the various algorithm for this. Another is a triangle finding problem, that also in another is a formula evaluation in this quantum walk. So, there are the various methods just to solve. No better quantum algorithm for this case are known until one was found for the unconventional Hamiltonian oracle model. So, the same result for the standard setting soon followed. So, another is the group commutativity, and these are also having the various complexity as well as the query which we use. So, there are the quantum algorithm requires various input and output. So, if we talk about the query complexity, it is less in the quantum algorithm. Moreover, there is another problem, BQP complete problem, that is also under the quantum walk. So, another is a computing not in invariants, that is also solved by better in terms of the quantum computer. Which can be simulated, which can be used to solve the problem in the polynomial form. Moreover, the quantum simulation that is nowadays used just to solve the problems before just doing the experimental. So, idea that quantum computers might be more powerful than the classical computer originated in the Richard Feynman observation that classical computer seems to be require the exponential time to simulate many particle quantum system, yet quantum many body system are able to solve themselves. Since then, the idea was a quantum computer can simulate quantum physical processes exponentially faster than the classical computer, and that has a great fleshed out and elaborated. Moreover, efficient, that is in the polynomial time, quantum algorithm have been developed for simulating both the bosonic as well as fermionic system, and these are used for the simulation of the other reactions beyond the capabilities of the current classical supercomputers by using only a few hundred qubits. So, by using these few qubits, some classical problems can be solved through the quantum computer in a very less time. So, quantum computers can also efficiently simulate topological quantum field theories in addition to its intrinsic interest. This result had led to efficient quantum algorithm for estimating the quantum topological invariant that can be any type of polynomial, as well as it may be invariant of the three-dimensional manifold. So, there are the various problems that can be solved by these quantum algorithm, that may be the hybrid quantum classical algorithm. Hybrid classical algorithm combines the quantum state preparation and the measurement with the classical optimization. Sometimes it can the feedback from the classical, the quantum will solve it. So, these algorithms generally aim to determine the ground state eigenvector and eigenvalue of the Hermitian operator. So, the part of this is the QA, OA, the quantum approximate optimization algorithm that takes the inspiration from the quantum annealing, performing a discretized approximations of the quantum annealing using a quantum circuit. So, it can be used to solve the problems in the graph theory. So, there are the various methods which there is an algorithm which when used according to its application, according to its objective. So, algorithm make use of the classical optimization of the quantum operation to maximize a objective function. So, another is the variational quantum eigen solver, means if we are having a variable values, so it can be solved. So, means this algorithm applies the classical optimization to minimize the energy expectation values of n state of finding the ground state of the Hermitian operator such as molecules Hermitian. It can also be extended to the find the excited energy of the molecular Hamiltonians. So, another is the contracted quantum eigen solver. So, there are the many many computational or algorithm that are used to solve the many quantum problems. So, another important point is the physical circuit, that is the quantum gates and the circuit. Just as classical logical gate and or not manipulate bits, quantum gates manipulate qubits through the unitary transformations. So, for this various gates can be used. So, in which we are having the common gates that includes the poly XYZ gates. These are there are the various gates in the quantum computation. So, in the quantum system, first is a poly XYZ gates, there is a quantum equivalents of the knot or rotation operation. Another is the Hadamard gate, that is H, that creates the superposition. Another is a C knot gate that creates the entanglement between the qubits. Whenever we are working on the entanglement, then we use the C knot gate. So, quantum algorithm are built using a quantum circuit which combines with these gates to process the information. So, they are the poly Hadamard and the C knot gate that has been used. Now, the quantum algorithm, some of the most famous algorithm that are the Shor as well as the Grover algorithm. Shor algorithm efficiently factors large numbers, threatening classical encryption system like RSA. Means Grover's algorithm, that is another algorithm that is the searches that search the unsorted or the unstructured database quadrically and faster than the classical algorithm. Another algorithm is the quantum Fourier transform, that is a QFT, that is a key building block for the many quantum computation. So, best known algorithm are the Shor and the Grover algorithm. That Shor for the used for the factoring and the Grover algorithm used for searching an unstructured database of an unordered list. So, Shor algorithm would, if implemented, run much almost exponential faster than the most efficient known classical algorithm for factoring and the journal number of the field 7. Now, likewise Grover algorithm would run quadrically faster than the best possible classical algorithm for the same task, a linear search. So, quantum algorithm can be categorized by the main techniques involved in the algorithm. Some commonly used technique ideas in the quantum algorithm including the phase kickback, phase estimation and the quantum Fourier transform, quantum walks, amplitude amplification and topological quantum field theory. So, all the algorithm that has been used for performing the various functions may be choose accordingly, and these ideas of the quantum algorithm for the various application like kickback, like phase estimation, like quantum Fourier transform, like quantum walk, like amplitude amplification, topological quantum field, entanglement, superposition. So, on the basis of that the various algorithms are designed and choose. So, quantum algorithm may also be grouped by the type of problem solved. The survey on the quantum algorithm for the algebraic problems. Shor algorithm is a quantum algorithm for finding the prime factors of an integer. So that can be used. That has been designed in 1994 by the American mathematical Peter Shor. So it is one of the few known quantum algorithm with compelling potential application and strong evidence of the super polynomial speed up compared to the best known classical algorithm. That is a non-quantum, that is a Shor algorithm. So however, beating the classical computers will require millions of qubits due to the overhead cause of the quantum error correction. So Shor proposed multiple similar algorithm for solving the factoring problems, the discrete algorithm problems and the period finding problem. So these are the most of the these are the feature of the Shor algorithm that can be used for solve the discrete logarithm problem. Moreover, the period finding problems, moreover the factoring problems can be solved by the Shor algorithm. Shor algorithm usually refer to the factoring the algorithm, but may refer to any of the three algorithm like period finding algorithm, like a discrete logarithm problem. So the discrete logarithm algorithm and the factoring algorithm are instance of the period finding algorithm, and all three are instances of the hidden subgroup problems. So Shor algorithm, as a name after the Peter Shor, is quantum algorithm designed to efficient factorize large composite numbers. So this is the definition of the Shor algorithm, and it is one of the most famous and impactful algorithm in the quantum computing, as it provides an exponential speed up over the best known classical algorithm for factoring. The ability to factor the large numbers has significant implications for cryptography, particularly basic RSA cryptography or the various cryptography. So the Shor algorithm can factor a composite number that is defined by the n in a polynomial time, specifically O log n power 3 compared to the which can be compared to the exponential time required by the classical algorithm, and this efficiency has made Shor algorithm a symbol of the potential power of the quantum computing and having a great interest to solve the cryptography, or it can solve the manious quantum attacks in this. So Shor algorithm has been used for the various purposes. Another is a Shor algorithm is more than just a method for factoring numbers. It is a foundational result that has shaped the field of quantum computing. It has inspired further research into the quantum algorithm complexity theory and the development of the quantum resistance cryptographic protocols. So Shor algorithm can be used for the quantum resistance cryptographic protocol. Shor algorithm represent a landmark achievement in the quantum computing by showcasing the potential of the quantum algorithm to solve the problem previously considered intraceable. So its discovery has had a profound impact on both the theoretical as well as the practical aspect of the quantum computing and the cryptography. So Shor factoring algorithm finds one of the two unknown variables that are crucial for efficiently factoring an integer. With these two unknowns in one equation, finding both values quickly becomes classical intraceable as the target integer gets larger. So whenever we are talking about the two, it is very easy to find out one, but the but the integers gets larger, means the database is larger, then it is not solved. So there are the classical algorithm to find one of these values, but they become the increasingly inefficient as the target integer gets larger. So if we are having a bigger database, then Shor algorithm can solve it. So Shor quantum algorithm finding that value efficiently if it is in the large integer the values, so it then becomes considerably easy to find out the other values also. Specifically, an unknown integer, that is g, when multiply by itself, then by itself p times and modulo divided by the integer n, we want to factor equations 1 by this value. So we start off knowing the number of n, wanted to factor Shor algorithm, estimate the p. First Shor algorithm first find out the p, the period of n, so we only need to guess the g. So using the smallest practical number n, which is if we take the 15, so Shor algorithm returns the p is equal to 4. So in this manner the value can be easily calculated by the Shor algorithm. How the Shor algorithm works? There are the many steps. The core of Shor algorithm is the quantum factoring transform, that is QFT. So a quantum analog of the classical transform, means whenever we talk about the Shor algorithm, then we use the quantum factor transform, that is the QFT, which is the analog of the classical Fourier transform. So how it works? So QFT allows the algorithm to find the period of a specific mathematical function related to the number being factored, as in the Fourier transform. So once the period is found, the prime factors can be efficiently extracted using the classical method. So the entire quantum component of the algorithm is the quantum phase estimation. Why it is a quantum phase estimation? As it is the prime factor can be efficiently extracted. So now here we are having a quantum phase estimation which incorporates the quantum factor transformation. So quantum Fourier transformation. So QPE, that is a quantum phase estimation, uses the modular exponential and the inverse of the QFT to estimate the phase of the quantum state. So classically, the information retrieved from measuring the circuit is then used by the classical algorithm such as continued fraction factoring to efficient determine the factors of the larger target. So so implications of the Shor algorithm, there are some practical implications of the Shor algorithm. So but Shor algorithm work efficiently. So the problem of factoring a large composite numbers into its prime factors is classically hard. So meaning that the time required to solve it grows rapidly with the size of the input. As well as the size will be increase of the input, the time period will be taken by the algorithm will be larger. So encryption, widely used in secure data transmission, relies on the difficulty of factoring the large number. So Shor algorithm, by efficiently solving this problem, possesses a potential threat to RSA and similar encryption schemes. So Shor algorithm complexity is exponentially more efficient than the known classical algorithm such as the quadratic sieve and the journal number of the field sphere. So Shor factoring algorithm also highlights the computational power of the QPE and QFT, which have application beyond the integer factorization. So one of the most talk about potential application of the quantum computing, for example, is the quantum chemistry QP, where we saw the Fourier transformation. So QPE can compute the ground state energy of the molecule with the same exponential efficiency advantages at its bestow upon the integer factorization. So what are the challenges and the limitation? If we talk about the Shor's algorithm is theoretically efficient, then its practically implications on the current quantum computers is challenging. So it requires a significant number of the qubits and error corrected operations. So efforts to implement Shor's algorithm have led to the variable insight into the quantum error correction. So algorithm optimization is also required in the Shor algorithm. Moreover, hardware development which can work perfectly by using this. So in fact, the size of the quantum circuit resulted in the discovery of the one of the earliest quantum error correction codes, also known by the Shor code. So to avoid the confusion, Shor algorithm refers to factoring algorithm, while the Shor code refers to the quantum error correction. So that would make it possible to implement Shor algorithm on the fault tolerance quantum computer. So fault tolerance can be done by using the Shor algorithm also. So Shor code and Shor algorithm both can be used in the quantum algorithm. Thank you very much. We will continue this lecture in the next domain. Thank you very much.